Hello everybody, welcome to today's webinar presented by Rogers Corporation with the subject Optimize integration of capacitors on a busbar to achieve the lowest inductance. My name is Dominik Pawlik, and together with my colleague Jan Daneels, we will be presenters. This presentation, as already said before, it will be divided into two sections. The first one we will have presentation running, and we will give you all the information about the subject of this webinar, and during the same time you can ask questions in the small chat window, and at the end we will be answering all your questions. So maybe before we start, a few words about as well presenters. So as already said, my name is Dominik Pawlik. I'm working for Rogers Corporation for more than 3 years, and I have a position of a product innovation manager, particularly for the busbar as well as for the capacitor busbar assemblies and all the related products to it. And my colleague Jan Daneels, he's an expert on the capacitors. He's been working for many years in this industry, so he has extensive knowledge about the different type of capacitors, and he will be sharing this knowledge today with you. That's shortly an introduction, and let's move forward with the presentation. A few words about the Rogers for those of you who are not familiar with the company. So Rogers is a global leader in engineered materials, helping power, protect and connect our world by addressing challenges of mega trends. The company was founded in 1832, and it has a long history of material innovation. And as you can see, the company is stock listed, employees approximately 3,400 worldwide. We have many manufacturing locations in 5 different countries. And myself, as well as my colleague, we are based in Belgium, where we have our design center, and we support our customers in Europe, but we have as well the design centers in Asia as well in the US. So they are supporting all the continents. Basically, what I would like to say is that the company is focusing on delivering really the technology products, and within this Rogers company we have different divisions. Very shortly about the 3 divisions that we have. One of them is Advanced Connectivity Solutions, and this is where we are manufacturing high-frequency laminates and the pre-bakes. Then there is Elastomeric Material Solutions, manufacturing silicone foams, fabrics, films, and foils. And the 3rd division that actually both of us are working is a Power Electronic Solutions called PES. And here there are 2 brands that are very known on specifically on the power electronic market. One of is ceramic. This is for our substrates business that goes to the power module. And then we have a Ronings. This is known for laminated busbars. However, since a few years we are offering on the market as well the capacitor busbar assemblies and all kind of different busbars for industrial applications. And with the recent activities on electrical vehicles or in the mobility, we have a complete range of products as well to offer to this market. So all 3 business shares focus on, of course, on the mission critical applications, and they focus on a unique engineering material solutions. If you would like to know more, then please go and visit our webpage, and then you can find some more details about the other divisions. Today, the focus of this webinar is to look at our capacitor busbar assembly and how can we optimize inductance specifically, since this is a very sensitive subject right now, specifically due to the new technology like a silicon carbide coming on the market. So a quick agenda. I will do a short introduction about laminated busbar overall, what is it. Then I have some challenges that we see on the market, so I'll just shortly describe it. Then of course we will go into the details about talking about the new development in the desealing technologies, and of course the subject inductance improvements, inductance measurements, technical overview of products that we are offering, simulations, some markets, examples, and we will have a final slide just give you an idea about our global technical support. So, as I said on the beginning, Rogers is known for manufacturing of laminated busbars. But actually, what is the laminated busbar? This is important, a question to answer it. So, laminated busbar is basically a multi-layer construction of the conductors, and they can be out of a copper or aluminum. Sometimes we use aluminum to reduce the weight in the inverter. In some cases as well used to reduce the costs. So these are the conductors, and between the conductors we have a thin dielectric materials, and all together we take it and we laminate it in the one structure. So as you can see on the first slide in front of you, we have copper layers, we have dielectric films. This typically we use PET or polyimide materials depending on requirements in terms of the temperature. Then we as a manufacturing, we give some guidelines, and then we laminate it with one structure. The big advantage of a laminated busbar is partials free. It is as well a low inductive element and used in a high voltage systems. From the electrical point of view, the busbar is a kind of a multi-layer electrical circuit, and of course its structure is used to connect on one side capacitors and the IGBT modules through the specific connections. So if you look at this electrical schematic, this line red and blue that goes to IGBT modules and to the capacitors, this will be actually the busbar. So busbars overall, they improve reliability, lower inductance, and from practical point they eliminate wiring errors in the inverter. So let's have a look maybe at a little bit at the challenges what we see right now. On one side we have a busbar that is a low inductive element, as I said, but if we look at the power electronics both in automotive and industrial applications, all they need to meet the challenging requirements. It's related not only to the inverter, but I think to all kind of converters in the different electronic businesses. So what we see definitely the requirements for reliability, high efficiency. This is a standard subject for all the designs of the inverters. On the other side, we have as well more compact design, increasing much more power density. We also have, as I said before, a lot of requirements in terms of inductance, specifically for the silicon carbide technology, when the semiconductor switches require much higher switching frequency. Since the electronic components and its hardware still becoming more and more complex, design solutions we have to find not only at the level of a component but at the system level. That's why we are focusing right now more on a system, and we look at two components like capacitors and the busbars. And of course capacitors, they are important during the semiconductor switchings, and they are a part of a commutation loop, so they have an effect basically on behavior of a complete inverter in the specific applications. And overall goal is to reduce this inductance, and that's something what you will see on the next slides. So in terms of a new development within Rogers and the Rawlings, we have been already offering on a market since more than 3 years a capacitor busbar assembly solutions with a different type of capacitors. Right now we have our own solution where like you see on this picture here, we have laminated busbars, and on the busbars we have integrated capacitors. We have as well connected on this example here IGBT modules, and for those of you who had a chance actually to visit us on the PCIM show in Nuremberg last week, and we have presented this model. Overall, this is an answer to requirements in terms of silicon carbide technologies, low inductance. We developed this product, and we use here some specific techniques how to connect capacitors or integrate capacitors on the busbars. We have patent ongoing. where we designed the busbar and the way how the, let's say, the part of the capacitors, the terminals are connected to the busbars in a low inductance mode. So you will see this a little bit later, maybe not into the details in this free webinar, but at least we will give you some indications. So this is the subject of this discussion. As I said, we are looking at overall low inductance solutions, and as we know, the current that is flowing not only through the busbars but as well through the capacitors generates some heat, and overall we wanted to reduce this heat in order to increase the lifetime reliability of the system. So what you have on this photo, actually, this is an example of capacitor busbar assembly that is used with a hybrid Pack 2, and we've been testing this and offering already to our customers. Here's an example where you see actually the capacitors, but it can be as well encapsulated, can has all this kind of features to connect this module to the other components in the inverter system. So let's move forward with, I think this slide will take my colleague Jan will explain to you how we can improve the inductance based on the busbar design changes.
Thanks, Dominik. Actually, there are two ways to reduce the inductance. First, we will try to reduce as much inductance in the busbar design. Here we have taken as example HP2. On the original design, with standard taps, here you are connecting the taps directly to the IGBT. We are having an inductance in the range of 14 nanohenry. When we are making an overlap of the taps, we are achieving an inductance of less than 5 nanohenry. We can also make a partial overlap, as you can see here. Then the inductance is a little bit higher, in the range of 5.2 nanohenry. Or the optimal design is that you don't have taps, but a straightforward busbar, and then we are having an inductance in the range of 4.8 nanohenry. So as you can see, by improving the design of the busbar on which the capacitors are mounted, we can also reduce the inductance. Also important, just to show, is also which kind of connections to the IGBTs we are having. If we are having a Z-band, as you can see here, this is giving a high inductance in the range of 32 nanohenry. When we are doing a small dishing in the busbar, then we are achieving an inductance in the range of 11 nanohenry. And when we are putting a small bushing on top, then we are achieving an inductance in the range of 12 nanohenry. So this is the improvement which we can do in busbar design. On the next slide, we will show you how you can also reduce the inductance by placing the capacitors in a special manner. What we have done here, we have made our coupling design, as you can see here. And here we are measuring standard an inductance of 15 nanohenry. We're also comparing us with competition. So we have selected a competitor 1 who is having an inductance of 23 nanohenry, and competitor 2 who is having an inductance of 27 nanohenry. As example here, we have taken the HP2 connection or the hybrid pack. Actually important for the designers is to know the overshoot voltage after 0.1 microseconds. Supposing you are driving your IGBTs with 120 amp, you can easily calculate it. So you are taking 15 nanohenry and you multiply it with 120 and you end up with 1.8 microvolt per second. You are doing that the same for competitor 1 and for competitor 2. Important is to know the overvoltage after 0.1 microsecond. So then you take the 1.8 microvolt per second, you multiply by 0.1 microsecond and you end up with 18 volt. For the Rogers design, the coupling design, our competitor is having 27 volt and competitor 2 is having 32 volt. So when you compare Rogers with competitor 1, you can say we have here reduction in overvoltage in the range of 30 to 40%. With competitor 2, it's in the range of 50 to 55% roughly. On the next slide, we will show you how we are measuring the inductance. Actually, these measurements which you can see here are done with a single pulse. So actually, we are charging the whole cap length system and then we are fastly discharging it, making actually some kind of a short connection And then we are measuring here the overshoot voltage. This is what you can see here. This is what you can see here. This is the overshoot voltage. This is quite important to calculate the inductance. As you can see here, it's in the range of, let's say, 14 to 15 volts. We have done where you're fixing your cap link onto the IGBT. So really in the center of the terminal, what we call. And on the test 2, we have measured closer towards the busbar. So we are measuring there closer to the capacitors. On the next slide, you will see our testing result. We have measured here a peak voltage of, let's say, in the range of 14 to 15 volts. Then you're taking the pulse load. It's in amps per nanosecond. So in this case, it was 0.7 amp per nanosecond. And then you can calculate out of this your inductance. So you take the 14.3 and you divide it by 0.7 and you end up here with an inductance in the range of 18 to 20 nanohenry. This is when you're doing it on the screw connection of the busbar. When we are measuring the inductance a little bit closer to the capacitors, then also the inductance will be lower. This is also measured here. As you can see, we are measuring here an inductance in the range of 16 to 17 nanohenry. This is done in-house, but we are having also a third party. We are also working with university on how to measure it in the correct way. You have seen the example on single pulse. On the next slide, we will also show you how we are doing it for double pulse. On the double pulse, actually what we have done here is that we have measured the whole design. So this is including the IGBTs, this is including the cap load, this is including also of your load. It can be a motor, it can be a drive. So we have done here the same. You are having here an overshoot voltage. You're also having here DEDT. And then we are calculating the inductance of the whole design. And this is in the range of 35 nanohenry. Then you're going to the data sheet of your IGBT driver, and there you find that it's 13 nanohenry. So at the end, you end up with a whole inductance of your cap link in the range, let's say, of 21 up to 22 nanohenry. Then the technical overview. The example which we have shown here is based on a film capacitor technology. We can also place aluminum capacitors on it or ceramic capacitors. It's up to you. The typical market range we are targeting for film capacitors is going from 10 microfarad up to 2000 microfarad. The typical tolerance for capacitor is 5 up to 10%. Since low losses are important, we are using metallized polypropylene film. Standard, we are aiming for designs with an inductance less than 10 nanohenry. Depending on the design, today we are having a few in production running who are having an inductance in the range of 2 to 3 nanohenry. So really low inductance is our major drive here. The voltages we are targeting is 300 up to 1500. We can go higher, but this is on request of customer. The currents today we are going from 200 amps even up to 800 amps. In our production, each time we are testing the cap link. How we are doing it? We are testing, of course, the capacitance, also the loss factor, also the insulation resistance, but also quite important for you guys is that we're also doing an overvoltage proof test. And here we are testing the whole capacitor bank at 1.5 times the rated voltage of the capacitor, and this during 10 seconds at room temperature, or what we say at 20 degrees. The rated temperature of the whole design is 85 degrees. Our climatic category is 40 up to 105. So this means the operating temperature is going from minus 40 degrees up to 105 degrees. How is the construction made? As already told by Dominik, it's an integrated laminated busbar on which we are mounting the capacitors. On request, we are also encapsulating the capacitors. This can be epoxy or silicone based. Also, if you are having a design in automotive, ACQ is also quite important. On request, we can also do it. So this means that the capacitors are ACQ approved and that we will test the whole coupling design also according ACQ 200. Also quite important is vibration. Standard according automotive is 5G, but we have the in-house capability even to go to 10G. So this is a short overview on what we are doing. I think Dominik will now take over.
Yeah, thank you, Jan. And I think what is important as well to mention is that we are actually not capacitor manufacturers. So we actually use the capacitors that are available on the market. We work with different suppliers of capacitors. We just basically make an integration in a low inductive way capacitors on the busbars. So as you've seen on the previous slides, there are different ways to do it. Definitely we as an experts in terms of laminated busbars, we can make suggestions how to improve the design of a busbar, and by taking another capacitor versus an active element and put it on the busbars, we create a kind of a subsystem, and we take care at least at the two components of our busbar and capacitors, because we have to know that the inductance contributors are definitely the busbar. There is as well a DC capacitors, and there are internal IGBTs, but as well different type of a connection, specifically between the IGBTs and the busbars. So yeah, we have this expertise in the creating this module actually, and with a low inductive way. Moving forward with our presentations, what we do actually as well, and we do all kind of simulations of inductance. So here's an example based on the previous example, where we run the inductance and we define the different current loops, and we evaluating as well the magnetic flux density. And here you have on the left side that we did the let's say the cross section of the busbars in a horizontal way or in a vertical way, and during the length. So we can make this simulation, and we can look for the areas where the inductance is the highest one, and then before we run actually the busbar or capacitor busbar assemblies into the prototyping, we already can theoretically, based on these simulations, we can see what are the critical area. And one of example how we can improve is, if you remember one of the slides before, we talk about the Z-band, we talk about the dishing and the bushing. There was mentioned by my colleague that with a Z-band we had an inductance around 32 nanohenries. By changing to the dishing, so basically the performing of the material, we could reduce it to around 11 nanohenries. Sometimes we are adding as well this bushing. However, bushing, if you think this is an external element, and this external on one side unfortunately creates there is additional inductance loop around it, but as well increase the cost. So this is kind of that we can do as well, if this is possible, to eliminate some of the components to reduce overall the cost of the DC system, but as well as reduce the inductance. So this kind of the simulations are done in-house by our engineers. Of course, next to the traditional inductance, there are as well the possibilities to make thermal simulations, and here is a good example of, again, on the same model where we run the heat simulation, and we put the 300 amps through the busbar and through this sub-assemblies. Maybe there's a little bit misleading, but if you look at the higher temperature actually is at the terminals level, so the ones that are the white, and you can see from the top and from the bottom. And you see on the right slide or right picture that there is a density of the current flowing through the busbars. Here the particle, what we have done it in addition to make sure that the terminals can handle the current that is requested, we actually change the thickness of this terminals by adding a piece of let's say a busbar, a smaller busbar, and it was welded to these terminals, as all this DC current is running only through these two terminals. So this kind of the simulations are a part of product offering, and we always work with the customers to optimize the designs using the simulations. As I said, this is very in early stage when the design maybe is not yet fixed, and it helps as well before we go to the prototyping and a mass series production to validate the product. Here are, well, very limited examples of our solutions. The busbars and capacitor busbar assemblies are heavily customized. There is no identical busbars. Every customer has a different requirements, different applications, and well, we can share only, let's say, only a really limited number of examples, since we have NDAs with our customers. So here what you see is on the top, these are the capacitor busbar assemblies used in electrical vehicles, heavy electrical vehicles. And on the bottom you have two real pictures of the busbars, one of the integrated capacitors, and then you see the busbars from the other side. When you see the soldering process, we have automated lines to make all this soldering in a high volume. And as I said, we are using a standard capacitors available on the market. Sometimes we have as well requests for the specific capacitors type. So then we work with different suppliers. We actually can advise as well in terms of what type of capacitors can be used. If, for example, if you have a pre-selected capacitor, but we see that in terms of inductance and the connections way we can optimize, then we can propose a different supplier. So these are the overall the product overall features. I have not mentioned so far the name of the product, but it's called Rawlings Coupling Solutions. And in terms of we talked about this already about the inductance. So it characterizes that it has a low equivalent series inductance and resistance, but we cannot forget about it, because the resistance has actually impact on the lifetime of complete system. It is a customized, very compact. We can make all kind of a configuration of capacitors on the busbars, a fully flexible design, and it is a highly integrated busbar design. In terms of applications where we see specifically this type of a solution, and it is related very much to the busbars. As I said, the busbars can be used in all kind of industrial application as well as in e-mobility. We looked at e-mobility for the bus trucks, but we don't want to limit it only to this application. So we have as well, of course, running solutions for the passenger cars. So looking at the voltage, we talk about 700 to 1000 volt DC capacitance between 800 to 2000 microfarad. For the inverters, definitely solar inverter, large inverters about 50 kilowatt. And depending on the region for US, what we see, and for Japan, capacitance up to between 500 to 1000 microfarad, voltage range between 1000 to 1500 volts, and for industrial drives, we have solutions as well between 700 to 1500 volt, and capacitance is similar actually to the ones that we see on e-mobility. These products can be fully customized, can have encapsulating, we are running it through different vibration tests and for the automotive grades, so very much depending. And as I said, we have expertise in both making designs, but as well in a high volume manufacturing of this type of solutions. So I know that this webinar maybe was very short, but we have a lot of documentations available on our webpage, and there is as well a specific design hub where you can find the product guidelines. So it is free of charge, and you can become a member of this design hub where you can download all the presentations. And I think this webinar will be as well available on if someone would like to listen it one more time. And so you will find the documentation about the busbar, about laminated solutions, about the integrated solutions, about these products that we just discussed. And I think this is the one of the last slides, just to give you an idea about our technical support. So Rogers, as I said, is an American company. However, we have coverage all over the world. We have facilities in Europe where we support our customers, and we have, of course, in Asia, in China, and Korea, and in Japan. So thank you very much for spending this few minutes with us, and now will be a time to answer the questions, the ones that you have actually put it on the chat, and we will be with Jana answering these questions. Thank you.